SwayamPrabha. Digital India. Educated India.
Welcome to lectures 4 and 5 of week 9. As like the previous lectures, here also we will be combining the lectures, 2 lectures into one, lectures 4 and 5, and the focus of this week was really to analyze in detail even more realistic perforated muffler configurations. So, we did cross flow configurations, alright. So, today also we will be dealing with couple of more configurations pertaining to cross flow type, and in one of the configurations, the second one that I am going to talk about today, we are going to talk about where we have 3 perforated pipes and an outer jacket or outer shell that is housing all these things. So, that will be quite realistic, and that is used quite a lot in the commercial vehicles. You will probably have a look at some of the only skim through some of the papers published of late regarding such double reversal and 3 perforated muffler configurations, and also possibly share with you some images. Now, before we sort of go into that, let us get back to our old friend, that is basically a configuration this. So, today is week 9 and lectures 4 and 5 of this week. Okay. This particular configuration, a muffler, and suppose we have such a kind of a thing, and this is expanding into a bigger chamber. So, this can be circular shape or elliptical shape or whatever it is. So, we have a flow, mean flow, that is coming in from this part. So, now since this is a dead end, the flow really has no option but to kind of navigate through these perforated holes and go through this. So, what is this element called? This is called a cross flow type, cross flow expansion. Okay. We make another such configuration, which is something like this, and so it kind of goes like this. You can sort of draw this thing like this, and this can be extended over a certain thing. So, this part is like a kind of resonator or something like that. Anyhow, the flow comes through the annular surface or annular portion, and it has no other choice, because this guy is a dead end. These are like the side end plates of a expansion chamber. Flow has no other choice but to go inside the duct, the perforated duct, through these perforates. So, it basically goes in something like here, and then it finally leaves the chamber like this. So, what is this configuration called? Very similar. This is called a cross flow contraction element, cross flow contraction type of element. Okay. Cross flow contraction. So, one question that comes to our mind is that what do we do with this element? How do we use them in practical muffler configuration? So, any guesses about that? So, this is not quite, this is an online class. So, we can't be really interactive, but there is something that you should probably have a look. I mean, you should try to think about different ways in which this configuration, this one, let us say 1 and 2 can be combined to form to constitute one muffler, and we are trying to take advantage of this cross or dissipative losses that occurs when flow has to basically cross through the chamber, through the perforated pipe, enter the chamber, and again enter into this thing. So, one such configuration which is quite popular is basically synthesized something like this. Okay. So, let me just sort of draw this thing in a greater detail. So, this will be like this. A flow goes through this thing and is again forced to expand or again enter back. Okay. And this is the, this guy is called the plug, rigid plug, and these are rigid plates. These ones, all right. This is called a plug muffler, a plug muffler. Okay. Let us sort of analyze or label the different geometrical dimensions of the plug. So, we will basically call, let us start naming this thing. So, we will call this as LP1 from here to here, and this is LP2. These means the length of the perforated section 1 and 2. So, the flow has no choice but to leave the chamber from here and then come back here. So, as we can recall from our last lectures, only for the sake of simplicity we assume that the grazing flow is sort of uniform all across here, and then there is some uniform bias flow across this thing, and there is a uniform convective flow across this thing, and then some uniformity is there everywhere. But if you do a proper computational fluid dynamic analysis of such flows in such bounded media in these mufflers, you will realize that this grazing flow gradually sort of decreases and becomes almost 0 here, and the bias flow tends to increase more towards this side, and then there is convective flow which is also non-uniform across along the space, and then the grazing flow inside this duct tends to increase as we go towards the end side. So, we can do a proper CFD analysis, but then there are segmentation approaches also which assume some sort of a linearly decreasing mean flow profile, which is more kind of complicated. But what possibly we can do is that we can assume, for the purpose or the sake of this course and not for research purpose, what we can do is that we can just assume things to be uniform, all right. So, mg, the grazing flow is uniform here, it is uniform here, and there is a bias flow that is leaving the duct, perforated duct, and entering the chamber, and it is here leaving the chamber and entering the duct, mb. So, this is assumed to be uniform, and there are some relations that we derived out of previously, we can use them. Now, what about the other things, So, let me use some other color. So, this is L1, this guy, this is L2, this is L3, this is L4. Okay. So, the net or the complete length of the chamber will be capital L is equal to L1 plus LP1 plus L2 plus L3 plus LP2 plus L4. And if we consider this as the chamber length D1, this is D, this is D naught. Okay. And we, of course, we sort of neglect the length of this thing, but you can actually consider the thickness of this thing to be T. You might just want to add T thickness here of the plug, TP, you can say TP. Okay. You will see the transmission loss of such a thing would be better than your simple expansion chamber, of course, and it would be sort of somewhere intermediate compared to the ECTR, that is your extended concentric tube resonator, but I say intermediate because it definitely has more, the amount of attenuation that is produced is much more compared to an ECTR, but at the same time there are more number of dips, the number of troughs and dips will be a bit more. So, let us sort of analyze such a configuration. So, this is clearly a 2 duct configuration, this one and this one and this one and this one. So, I need not write down the equations again for this thing, you can have a look at the previous slides, it is the same 2 duct interacting thing. However, what needs to be done is possibly going back to configuration 1 and 2 and writing down the appropriate boundary conditions for such a thing. Okay. So, writing down the appropriate boundary condition is a must. So, we will see how do we will go back to configuration 1 and start sort of writing down the appropriate boundary condition. So, there is one small thing that I need to do. So, this is, let us call this length L B, unperforated length, this is L A, and this is L. Okay. So, this is L. What we will do is that we will write down relevant boundary condition in this figure itself. So, let me sort of just put one here. What happens at the section, let us call this as 0, and this is L. So, this is duct 1, duct 2, let me write it with red color. So, this is easy. So, you have Z 2 0 is equal to P 2 by minus U 2, because we have to reverse the sign. So, this is minus j rho naught C naught cot into cot of K naught L A, and Z 1, that is for this duct, it is at L. So, this is U 1 0, and this is minus j times rho naught C naught cot K naught L B. Okay. So, this is what we sort of get, okay, for this cross flow expansion type of a configuration. So, these are the boundary conditions. So, one can, once you apply that, you can relate the variables at this section 0 somewhere in the duct here to the variables here, and then once you relate the transfer matrix, get the transfer matrix at this point to this point, let us put this as P 1 at 0 is equal to some T matrix, T 1 matrix times P 2 at L. Okay. And then similarly, if we go back to, if we go to such a contraction type element, let me sort of rub this. So, what are the boundary conditions? This is again your Z is equal to 0, Z is equal to L. So, what are the boundary conditions? So, this is duct 1, duct 2 as usual. So, this will be Z 1 is equal to P 1 0 this thing, and this is your L. Cot K naught L A. Okay. So, these are the two boundary condition, and at the end of the day what we really need to do is that sort of relate the transfer matrices. Basically, for a reversal chamber kind of a configuration, what we need to do is that basically get the transfer matrix from this point right up to this point. Okay. So, we can write things like P 2, what was the previous one? The previous one was of this form. Actually, there should be P U 1 here also and U 2 stuff here also. So, that is understood, but still. So, let me call this as T 2 matrix, okay, and this is P 1 U 1 at L, and in the intermediate one. Now, the thing is that once having obtained the transfer matrix using these boundary conditions, from this point really to somewhere here, and from this point really to somewhere here, the intermediate transfer matrix, this one also has to be obtained, and right, and these are the anyways the cavities that are formed. So, this particular stuff, this is already taken care of when you apply these boundary conditions. So, all we need to do is basically for a plug type muffler, which is very practical implementation of such a thing, we just simply need to multiply, let us say P 1 U 1, of course, there will be rho naught C naught stuff here at 0. So, this will be T 1 matrix and T intermediate, that is basically nothing but expansion chamber kind of a stuff will be there, and T 2 will be there, and P again P, but at a different location, say L, you can say L. So, these boundary conditions T 1 and T 2 already incorporate the boundary conditions for the resonator kind of a thing that we sort of see here, and the resonators formed somewhere here, and resonators that are formed here, and here in this thing resonator that is formed here, and in this part, and as well as in sort of this part. So, we just need to simply multiply the transfer matrix to get the plug muffler analyzed, and maybe we can consider some end corrections also. I have not talked about end correction, but there are certain expressions. I will just give a glimpse of that later, but what we need to do now is really basically go to the MATLAB code for doing our relevant stuff. So, for such a muffler, so let us go to the MATLAB code. So, let us first analyze in the commented section. So, there is one thing that I want to talk about doing a good coding stuff is that you should be knowing, whenever you code, you should be basically giving a lot of comments like the ones that you see here. There are a lot of comments. So, this file was written some time back, but I can still exactly know what part of the code is doing what just because I have put appropriate comments. For example, let me very quickly walk you through the code. The convective effects for mean flow is ignored, is sort of neglected in the big interacting two duct interaction matrix. There also have ignored the convective effects, as you will see from these expressions. I really have not done B inverse A. It is just I am happy to have some sort of algebraic simplifications at the expense of a small error in the computations, or rather than breaking my head and doing that. So, the dissipative effects, as you know, are much more important. It lowers the peak and increases the trough, raises the trough. So, those effects are seen. Now, let us quickly have a look at the configuration. So, D1 and D2, D1 is the diameter of the cylindrical shell containing the perforate assembly, that is your, what am I talking about? I am talking about this D0. Well, the symbols used in the code are sort of different, but still shell means the entire thing that you see, the entire thing here. Okay. So, now going over to the MATLAB code, D2 is the diameter of the cylindrical shell, D1 is the diameter of the uniform perforated pipe. So, the length is uniform, and forget about this LA, this is something, I do not know why I have written this. So, save the guy. L1 and L4 are the lengths of the resonators at the ends of the inner tube just adjacent to the perforated section. LP1 and LP2 are the lengths of the perforated sections. So, they are, there is a flexibility of choosing different length, and as usual DH and TH or T is the thickness of the perforate parameter. So, I will not explain that. So, but basically what is important here is L1 and L4 are the lengths of the resonators at the inlet and outlet. So, let us go back to the thing. So, following the same convention as MATLAB code, L1 is the length of the resonator here, L4 is here, L2 and L3 are the, this guy and this guy are the length of the perforate adjacent to the length of the unperforated section, that is a solid pipe or resonator formed due to the pipe itself just adjacent to the perforated section, is not it. So, just have a look at the length of the inner tube just adjacent to the perforated section, LP and L1 are the lengths. So, if you go back LP1 and LP2. So, that is the sort of thing that is there in the code, and I have assumed certain grazing flow I have just set it to 0 here, and bias flow is of course 0, so stationary medium. So, I have used Elnadi's expression, which I sort of trust more, the modern day expression. So, the T matrix for the perforate section is found out and boundary conditions are applied. It is going to be pretty tedious, so I am not going to walk you through the entire thing, but this is what we get, and then this further simplified and some inverse matrix is calculated to get it in this form, it was P2, that is this thing. And next, now for the coding for the second perforated section after the plug. So, we get this, and then we again have to apply boundary conditions and invert the matrix, and then this is the intermediate transfer matrix relating the upstream downstream variables, and then you simply multiply as I have shown, and then you finally sort of put it in the PV form rather than P0 to not that kind of a form, and this function gives the output of a final transfer matrix, which is obtained here, and then you get your this thing. Okay. What are the parameters? Ideally you could have done it in the file, but what we could do is that this is going to be a little sort of tedious. So, I sort of would not do that. Bear with me for a minute and I make some changes in the code. So, what I have done is that basically I have made some small changes in the code, not much, instead of just entering these values in the same file, whenever we need to do parametric studies, we simply need to change these values without having to bug the user. Before I hit run, so inner perforated duct diameter is 40, and I guess I have made a mistake here. So this D2 was, this D2 cannot be equal to this thing. So D2 is the diameter of the cylindrical shell, my mistake. So what I am going to do, let us say this is about 150 mm, and this can be actually a bit more also, 50 mm perhaps, and L1 and L4 length has the same 0.2, 200 mm. Perforated section is about only about 100 mm. You can make it more, you can make it something like 150 mm, and the lengths that are formed just adjacent to the perforated pipe in each tube is 100 mm, 100 mm each. 30% porosity, you can use a smaller value. It is known to cause a little bit numerical instability. So, there is a lot of scope of research also. We will talk about that in a bit. So, I have hit run, the code is sort of being executed. This is the transmission loss for ignore the peaks, they are sort of a little abnormal in the sense that you do not really have that much attenuation, flow will always dampen the things, and anyways we are interested not exactly in the amount of attenuation produced at the peaks. So, but one thing is there, that for such a chamber, this thing, this will be holding good at least for about 1000 hertz or so. I am giving you a rough idea of the cut on frequency. You can anyways estimate it using the K naught R naught is equal to 1.84, or in this case it's because it's axisymmetric, it's probably K naught R naught is equal to 3.83. So, you can find out by taking the value of R naught corresponding to 150 by 2, 75 mm and 343 sound speed, you can get a decent idea of the cut on frequency of the first mode, beyond which things will deteriorate. So, until that thing happens, what we can sort of do is that we can we can consider the performance transmission loss predictions using this one dimensional plane wave theory seriously only until about 800 to 1000 hertz, beyond which deviations are bound to occur, they will not be that much accurate. Now, we have done this and porosity value was set as 15%. Now, what we could do is that we have not really considered mean flow in this thing. Let us consider a small amount of mean flow. So, the transmission loss expression will not change, because 1 plus Mi plus 1 plus Mo value, that will be same, because the diameter of the plugs are the same, or the perforated pipe are same. So, let us consider a small amount of mean flow. So, there will be grazing bias flow also using this expression. So, I will do hold on, and I need to change the color in the code and put R stands for red. Peaks have started to come down, troughs have raised, the same phenomena happening over and over again. So, we will sort of give a little higher value, let us say we give 0.2 and plot this guy in perhaps blue color. Now, interesting thing that has happened, that the troughs have raised, there is no the peaks are no longer that sharp, they are kind of much shorter and fatter, they spread out, but the troughs have raised. So, mean flow definitely has a leveling effect, we can clearly see that, and basically you still get decent amount of attenuation even in the very low frequency, as much as 35 dB, 40 dB, flow really guides. So, there is no flow separation noise that would have otherwise occurred, and these kind of things are there. So, it is all good. So, and this is incidentally the same kind of a behavior that we see published in the literature when we have a plug muffler analyzed, these kind of domes and troughs, and then there are peaks based on the length of the resonator that will also be sort of formed. So, we consistent with what we sort of expected. Okay. Now, there is one thing that I wanted to sort of tell here, a general comment about the analyzing the perforated sections. So, basically what I am trying to say is that you have your expm command that you are using in MATLAB, like 15-20 years back, when computational power or such functions were not that readily available, you still have to solve that x dash is equal to Ax matrix. So, eventually to find out expm exponential of a matrix, you need to find out the eigenvalues, eigenvectors. So, xi into diagonal matrix of the eigenvalues into xi transpose, where xi is the eigenvector matrix. So, we need to write those routines or use some linear algebra package in Fortran or stuff like that. So, those are the standard techniques that you use, and MATLAB has quite good inbuilt solvers. But the fact of the matter is that we still have the problems when you use expm command for certain parameters. You get these sort of a wavy kind. Let me go to the presentation here and talk about what I mean is that typically you get this kind of a values and something like this. Now, for certain parameters this starts to do this and then it kind of stabilizes and all that, and suddenly you see for some parameters increase is doing completely garbage it is giving, and this is probably not the thing, but what I am saying is that you get rapid oscillation, something like this, this massive instability, numerical negative transmission loss and all that. So, these are really your numerical artifacts. The expm command also is not able to probably kind out for the length considered, because eventually you are doing expm minus a into L. So, basically for a much larger length you have problems. So, there is a decent enough scope of some additional investigations to be carried out in future in this thing. So, what probably could be done is that you could, instead of directly using expm command, there are things like boundary condition transfer algorithm published in the paper by Trinathkar and Munjal in JASA, Acoustics Society of America, several years back. So, there are techniques where you could do that sort of a thing, or possibly consider a better alternative to using expm command by using some numerical sort of techniques. These are eventually at the end of the day these are all constant coefficient ordinary differential equations, coupled one of course. So, you might actually consider using some sort of a one dimensional finite element scheme, or maybe one dimensional finite difference schemes with good frequency resolution, wavelength resolution capacity. So, those kind of things can be done, or some special novel techniques can be done. So, the reason that I am telling you this is because all mufflers, all commercial mufflers, let us go to Google. What we need to do is that just have a look at some of the commercially available muffler interior, commercial muffler interiors, and you will see invariably the presence of perforated pipes in all the mufflers. So, well, these are some of the perforated things, but let us say muffler cross section. These are simple Google images that I am trying to show you just right now. So, these are some of the schematics, but what I really wanted to point out is that maybe some nice cool photographs you can have a look and sort of appreciate for yourself. What is it like? So, well, let us say this is like a old and worn out muffler, but this is a YouTube video it seems, and so the point is that there are so many of them. Well, all of them have perforated thing. Let us have a look at this thing perhaps. So, these are on a different kind of a perforated holes, basically in a central pipe through which the waves are allowed to interact with the annular cavity, which is filled with an absorbent material. So, this is something we have not really seen so far. Maybe this is a nice cool photograph in Pinterest. The comes in here and interacts with the annular cavity. There are two interacting ducts that you sort of see here. Then there are this is yet another one. So, in the cavity there is a U-tube bend, there is a U bend here, things like this, and then there are so many heaps of them. All of them have perforated pipes. So, what exactly am I trying to say here? Invariably they always have perforated muffler, perforated elements, like as you are seeing here, and in these this is a nice photograph from some commercial company. So, this is the one that a 3-pass muffler configuration flush tube, what we would be analyzing, just to give you a glimpse of how it works, and also have a look at some of the photographs. They are unequal perforated patterns. You can do a lot of things, lot of parametric studies, and completely thoroughly analyze it, and these are end chambers which kind of facilitate flow reversal, and waves propagate typically along the major axis, not along the axial length, for such short upcoming book that is almost published now. And so, the point I am trying to make, well, you can keep looking at these photos on the internet at your leisure. The point I am trying to make is that there are so many muffler components, so many configurations which have it becomes quite important for us to analyze or pay great attention to the accuracy of our transmission loss predictions for commercial mufflers given their popularity. So, either we need to develop codes which can resolve this numerical artifacts or numerical instability issues that typically happen, as we are seeing if we just change the parameters beyond a certain range, using some numerical scheme like finite elements or perhaps a finite difference, as I was mentioning about, and maybe kind of instead of just using the expm command in a very brute force kind of an approach, one could do a lot of other things as well, maybe divide the sections and then maybe do some kind of a cascading and properly analyzing the round off errors that are happening. So, this is sufficient room for computational accuracy of such systems. So, one really needs to think about analysis of such a system. Now, we probably would like to go to 3-pass perforated duct mufflers. So, these are some of the photographs that you had seen just here. So, this is the 3 duct perforated muffler which is flush tube. So, let's first also have a look at some of the nice papers that have been published in this thing. This is a very practical commercial muffler. Let me draw such a configuration for you, draw this 3 interacting ducts thing. So, here we are and there are 3 ducts. So, these are all perforated. Something like this. So, what really happens is this is called a pass tube, So, this region, this can be elliptical in cross section or possibly circular in cross section, does not really matter as far as plane wave analysis is concerned, and then you have your this kind of a thing. So, I will rub this guy and draw this thing here again. So, the waves really flow really comes here, and the waves are it's kind of going, the flow is allowed to, is forced to take multiple things. So, this is called a double reversal, the first reversal, second reversal, and this is called a 3-pass thing. So, this can be perforated throughout its length, or it can be partially perforated forming cavities here and here, resonator cavities, much like your extended ECTR element. And here this length is pretty typically quite short, L1 this is much more shorter than the cross dimension, let us call it D1, assuming this to be elliptical in section. So, L by D1 is typically about approximately 0.2 for commercial mufflers. So, because the space is really limited, most of the space is occupied by this entire thing. Okay. So, waves typically go along the major axis rather than going like this. Okay. So, they do not travel like this, they travel in this manner, but this is this is really the least of our concern now. Right now our concern is basically to figure out this 3 duct or actually 4 duct system, and eventually you would end up with a matrix which resembles something like this. So, this is going to be your pretty heavy duty matrix. So, if you choose to number this as duct 1, 2, 3 and 4th is the annular thing. So, P1 rho naught C naught U1. So, this is your DD Z being the length measured in this direction, and P4 rho naught C naught U4, and this is your this thing. Okay. P4 rho naught C naught U4 and this kind of a thing. So, you really have 8 cross 8 matrix. So, and then this we are gradually moving towards what is called a network analysis. So, that will be the part of the next week 10's content, but before let me just tell you something, that such systems become algebraically very tedious. So, instead of we definitely do have boundary conditions somewhere across this section and across this section. Eventually what we would want to do is that get a transfer matrix relation between the points just here, this one, this guy, and relating kind of sort of all the pressures and velocities here with those possibly at this point and this point, isn't it? And assuming that these ends are rigid and you have some sort of a resonator cavity formed in here. And then once you from here to here is a simple tubular element transfer matrix, same thing from here to here, and eventually we would also want a transfer matrix that is relating things somewhere here and the one that is related here and here, and these tubes are flush with this end chamber. They need not be, the length can be actually more also depending if the space is available. Typically it is not. If the more space is available, you can have things like this here, or you can typically have a whole cavity here. So then you will have multiply connected muffler. Right now let us analyze this thing a little more carefully, and what we typically do, that the waves are allowed to interact with the annular duct through these holes, but they are also allowed to go through this thing. So the flow however can take only one route, it has to bend through these things. Typically it bends, one must still do a CFD analysis, but what I am trying to say is that even in this there is an element of multiple connections. You definitely have multiple connections. Suppose this guy wasn't there, suppose this pass tube wasn't there, okay, you would just have this kind of a thing. Then definitely the waves, this is for sure cannot be analyzed using a simple transfer matrix cascading approach as the one that we are going to talk about now, but this is a multiple connection thing, if the pass tube weren't there. But suppose this pass tube is here, then definitely this is a non-multiply connected muffler, but with certain amount of interactions are happening parallelly between the waves that are here and this cavity and the waves that go here. Eventually since transfer matrix cascading can be used here, the point I am trying to make is that at the end of the day it is going to be pretty tedious. The first things first, we need to analyze or relate basically pressures P1, P2, P3, rho naught, C naught U1, rho naught C naught U2, rho naught C naught U3 here with the ones at this section at Z is equal to L, including incorporating the boundary conditions that is here and here, resonator conditions. Get the transfer matrix between this point all the way until this point, and similarly the transfer matrix between this point and this point. So we have transfer matrix between this point and this point, this point and this point, and the entire transfer matrix between relating 1, 2, 3 at Z is equal to 0 with variables at Z is equal to L, and then this is a simple tubular element, and the transfer matrix between this and this really incorporates all that is happening inside this cavity and this cavity. So all that simple algebra, but it can still be, you can do some sort of a cascading approach and get the transfer matrix between this point and go about finding out the transmission loss of such a muffler system. So I like to go to a paper. This was your analysis of an extended tube 3-pass perforated element muffler by means of transfer matrices. So the configuration that was analyzed was pretty much what I am talking about, except that the thickness effects of the end plate, the plates that demarcate or separate the perforated region between the end chambers have the thickness of such a plate has been considered while computing the transfer matrices. So now what is happening really is that this is a multiple interaction duct. So I am just going to rely on this paper, and a subsequent journal article was also published, but this is making use of the generalized decoupling approach. Well, at that time it was a generalized decoupling approach, but what I am saying is that this entire thing, once we get it in this form, for us it is a matter of using this command and relate upstream and downstream variables, maybe like I was just hinting at, developing clever numerical or computational strategies to analyze such things within the context of a plane wave analysis also. So plane wave is not all that bad. Once we get S1, S2, S3 and S1, S2, S3 at 0 and LP, where S1 is your pressure and volume velocity, or rho naught, C naught, U naught, velocity. So once we get such a representation between 0 and L, and then we have our transfer matrices. So if you have a look at this thing you need to have a transfer between this point and this point and this point and this point. So, so I am just trying to walk you through the derivation here. So, I may not go through each of them in a great detail, but just skim doing the derivation. The state variables at Zp in duct 1 may be related to those in duct 2 to right end cavity, that is in figure 3. The right end cavity means what? This one. So, between this point and this point, incorporating the tubular elements, and there are some end corrections also in the length of the pipe, which is okay. So, you get this relation, and then you get relation between the left end cavity like this with certain end correction lengths, all those things are there. And finally, S10 is related to S3LP. You know, eventually what we want, let me go back to this figure, we want relation between pressure and velocity just somewhere here to those somewhere here, and then it is a tubular element, so it does not really matter what happens, no matter the length, whatever the length is. So, that is what the author has done by cleverly doing some clever algebraic manipulations. He has found out that S10 is related to S3LP using a C matrix. C matrix is a big D, A, W, and all these matrices are there, where your this matrix is your sub matrices really. So, it is written in a certain fashion. So, I will probably write, I mean I will show some MATLAB coding results, and W is your this matrix, C is this matrix. So, I am sort of not going into the algebra because of want of time, but there are some parametric studies, the result of which I would sort of show. So, I am assuming Mach number 0 only, he has considered 0.1, and there are some nice cool results that the author has published here, and then you have a longer chamber with tubes protruding inside, and then a transmission loss, which the good thing about such configuration, such perforated thing is that the reason why do we use such a muffler, because in automotive mufflers we do not have really much of a space, and the flow within the constraints of a limited space, and with the understanding that you can tolerate a much higher level of back pressure, you are trying to bend the pipes multiply, so that the flow, allowing the flow to go through number of perforated holes and taking a number of turns, so incurring losses. So, back pressure will be more, but it is not that much, because you have number of interacting ducts, but at the same time, because waves are allowed to take a larger path through perforated sections and resonator cavities and all that, you would expect to have a number of peaks and sort of domes or things like that, eventually with the understanding that you hope to get some sort of a broadband, at least some 10 dB, 15 dB constant attenuation at beginning from very low frequency. So, that is what plane wave analysis parametric studies promises you. Just vary the parameter and figure out one of them, which gives you a good estimation, and so this is one of the curves that we get, broadband transmission loss, and so these kind of things happen here. So, we do get such a transmission loss configuration. So, now the thing is that let's do some MATLAB coding for certain parameters like LA, LP. LP is a perforated length, LA and LB are the length of the 70 mm or 100 mm are the length of the left and right cavities. This is connecting length just about 5.5 mm or something like that. Thickness of the pipe, porosity is only about 5%, radius of the duct is something like this, thickness of the pipe and the hole diameter. So, those are some values, and this, like ever since this paper, and this is probably another such configuration, such 3-pass muffler configuration with circular cross section, exactly the one that I am talking about, analyzed in COMSOL multiphysics, and they did some finite element modeling, full 3D modeling, and figured out some transmission loss curves and all that, published in 2018 really. So, yeah, so all good, and then you have yet another paper with perforated bulkheads published in here. So, there are a number of such sort of advancements that has really happened. So, what we will do is that we will quickly jump on to a MATLAB code, and let me also open the common perforated, carefully have a look at, these are all standard parameters, by now you should be familiar. Alpha is some value what I used in the last code, so, net effective annular area, and this is the perforated impedance, some value to give the perforated impedance. Now, this is an 8 cross 8 matrix, okay, exactly what I was talking about, momentum equation, continuity in the duct 1, in the duct 2, duct 3, and finally you have duct 4 where you have such a thing. All these effects are there, mean flow has not been considered, and finally you get exp m times thing and get it in the PV form, and possibly with some rearrangement I guess, or probably not, and then applying the impedance conditions at the left and right of the thing, and then relating and then sort of reducing it to the 6 cross 6 thing, and finally what you get is a 6 cross 6 matrix. So, this code computes a transfer matrix in the state variables forms from upstream or the downstream to the common perforated section after applying rigid wall boundary conditions for the annular shell. So, here note that we are not applying the if you go back to the presentation, and so here when I talk about boundary conditions, I really mean applying the boundary conditions here and here, I mean pertaining to the rigid end here. So, this is at this section, this is at this section. Okay, so that is what I do. So, MATLAB coding can be fun, provide that you know how to do it and keep manipulating things, and then once we get that, the overall transfer matrix is exactly what following Munjal's approach in this paper. So, you can follow other, you can, so this particular configuration allows you some sort of a cascading or simple multiplication of transfer matrices. Network analysis, when you have multiple wave propagation paths, we will study about that in the next week, like I said, by introducing some simple elements to begin with. But for now what I suggest is, let me just run the code. It is going to take some time. Let me sort of increase the value, let us say 5 hertz, because this is going to take some time, and maybe do only up to 1000 hertz or maybe 1500 hertz. So, let me also bring out the porosity value. 4.5% is the porosity really, thickness is 8 mm, diameter of the hole is about 2-3 mm or something like that, thickness is 127 mm, and LA cavity, LB cavity is about 150 mm and 102 mm. That is basically the end chambers that is at the left and the right given by these lengths, and this is the length of the common perforated section, I guess so. No, so this is the length of the common perforated section, my mistake, and LA and LB I have to see what it is. Diameters of the duct, diameter of the shell. So, I am doing choice 2. So, it might be because of some changes in the code I would have done. It has been some time now that I have used this code, but let me get some nice curves. So, beginning from 5 hertz up unto 1500 hertz, let us see what we get. So, this is going to take about 300 runs or 301 runs. So, we should be getting something like this kind of a curve that we sort of got here, this kind of a broadband. We are setting, of course, mean flow is not considered really and we are just considering the perforated impedance by the classical one, not using the LNRD's one. One thing is there, while the code is executing, one piece of advice is that whenever you write codes, again comment it and kind of securely save it at different location, and you never know when you will use certain things. So, like this you can actually, I would encourage you guys to actually the ones who are interested to build your own library of muffler elements. That is what all muffler consultants they do. So, while we were talking, a transmission loss curve, a beautiful nice TL curve has popped out, and you see exactly the same stuff. So, we are able to sort of reproduce what the author has done in this paper. Of course, this is with mean flow, effect of distance. So, this is with mean flow. We have not really considered mean flow, but we know for sure what is going to happen when mean flow is there. This peak will come down and this trough might be raised a bit, especially this one, and this would be further. There will be leveling effect, we know by now, we should be knowing, but what is to be seen, we are still getting about roughly we would easily get about 8 to 10 dB, 8 dB transmission loss up to about 1000 hertz, because especially when flow is there, because this will raise the trough, no doubt about it. These kind of things will happen. So, this configuration presents nice insight into the actually used commercial mufflers, and with this thing what we will do, we will stop for the day and I will see you in the next week. But on a parting note, what I would allude to is that in the next week we are going to talk about the impedance matrix concept for the first time. How do we, all this while we are characterizing things in terms of pressure and velocity at one port to the ones at the downstream port. It was really, at the end of the day, you would have got even something like 2n cross 2n matrix, or for a simple case 2 cross 2 matrix. But you can have ports with 3 ports, single inlet, double outlet muffler. So, how do you relate that? How do you characterize such a system? So, by characterization I mean relating some state variables to the other state variables using some sort of a matrix representation. So, there should be some relation between them. For a general n port system, n need not be an even number, n can be odd number, 3 ports, single inlet, double outlet, or double inlet, triple outlet, things like that. So, you need to work in impedance matrix which is more general and is used a lot in electrical theory. So, there is a, like we have been talking about electroacoustic analogy. So, here also again impedance matrix. So, we will talk about impedance matrix characterization in the next week and how to analyze fairly complicated and pretty formidable looking system by means of a network analysis where each of the mufflers, at least the 2 ports one can be characterized using the transfer matrices, but need not be. You can use an impedance matrix depending upon what you want to do, and then you apply junction laws and characterize such a thing, and possibly use such an network representation, talk about different elements which involve multiple acoustic wave propagation paths, for example, a Herschel-Quincke tube, before moving to this multiply connected perforated thing element. So, we will analyze such a thing, and if time permitting we will also have a look at some of the recently published ideas like integrated transfer matrix, which can be used to analyze very complicated commercial mufflers. All within the realm of plane wave we could analyze such complicated multiply connected mufflers, and time permitting we probably would also be going to a CCTR configuration. Remember the things that we probably discussed I think in week 5, if I can see my notes, is we probably discussed that in I guess in week 6, I am sorry, my apologies. So, we did only conical mufflers, but we can probably have a central pipe with a perforated thing and with extensions, but the outer or the annular thing is no longer uniform in shape, it is conical in shape. So, we have a CCTR, conical concentric mufflers, which can also be analyzed using a matricent approach. So, let us see how we go about doing that, time permitting. So, this is all going to be the focus of the week 10, and till that time I would strongly encourage you to start writing your own codes and developing your own libraries for the plane wave thing. It will be a very useful exercise for you guys if you want to really learn things from the from the coding point of view, at least from a designer's point of view. Okay. So, this is one aspect that you should have, good analytical and computational skills, and and then there are of course people who do experiments, so they are good at that. So, till that time I would stop here, and I would see you in week 10 with the contents I described below. Thanks.